Download this code from codegive.com, link in the description below. OK, let's dive deep into implementing an in-place bitwise Radix least significant digit, LSD, sort for a linked list. This is a somewhat advanced topic, combining linked list manipulation with a specific sorting algorithm, and doing it in place adds another layer of complexity. I'll break it down step by step with explanations and a complete code example in Python. Understanding the problem. Linked list. A linked list is a linear data structure where elements, nodes, are linked together using pointers. Each node contains data and a pointer, or reference, to the next node. The last node's pointer is typically none or null. Sorting. The task is to rearrange the nodes in the linked list so that their data values are in ascending, or descending, order. Radix sort. Radix sort is a non-comparative sorting algorithm that sorts elements by processing individual digits, or bits, of the numbers. It avoids direct comparisons between elements. LSD, least significant digit. LSD Radix sort starts sorting from the least significant digit / bit and proceeds towards the most significant digit / bit. Bitwise instead of processing decimal digits, will work with the bits of the numbers. This is suitable for integers and potentially floating point numbers, if you understand their bit representations. In place. An in-place sorting algorithm uses a minimal amount of extra memory. We aim to rearrange the nodes of the linked list without creating a large auxiliary data structure like an array or a new linked list. Why is this challenging? Linked lists and Radix sort. Radix sort is often easier to implement with arrays because arrays provide direct access to elements using indices. Linked lists don't have this direct access, you have to traverse the list to find specific elements. In place linked list sorting. Modifying linked lists in place requires careful pointer manipulation. You have to keep track of the head, tail, and next pointers of various nodes to avoid breaking the list or losing nodes. Algorithm outline. Here's the general approach for the in-place bitwise LSD Radix sort on a linked list. 1. Determine the number of bits. Find the maximum value in the linked list. Calculate the number of bits needed to represent this maximum value. This determines how many passes the Radix sort will need. 2. Iterate through bits, LSD to MSD. Loop from the least significant bit, bit 0, to the most significant bit, the bit corresponding to the maximum value's bit length. 3. Partition based on bit for each bit position. Create 2 buckets or groups, one for nodes with a 0 at the current bit position and one for nodes with a 1 at that bit position. Iterate through the linked list. For each node. Extract the bit at the current position from the node's data value. If the bit is 0, append the node to the 0 bucket. If the bit is 1, append the node to the 1 bucket. Crucially, do this in place. You'll need to manipulate the next pointers of the nodes to move them between the buckets. 4. Reassemble the list. After processing all nodes for a particular bit position, reassemble the linked list by connecting the 0 bucket to the 1 bucket. The 0 bucket should come before the 1 bucket. Update the head and tail pointers of the linked list. 5. Repeat continue this process for each bit position, moving from LSD to MSD. Code example, Python. Explanation. 1. Node and linked list classes. These are standard linked list classes for creating and manipulating the list. The linked list class includes an append method for adding elements, display for printing the list, and get_max to find the maximum value, used to determine the number of bits to process. We also maintain a tail pointer to make appending more efficient. 2 bitwise underscore radix underscore sort, function asterisk. This is the core of the implementation. Asterisk initialization asterisk. It starts by finding the maximum value and the number of bits required. It handles the case where the list is empty or contains only zeros. Asterisk outer loop, bits the 4-bit underscore index in range, number underscore bits, loop iterates through each bit position from the least significant bit, 0, to the most significant bit. Asterisk bucket initialization asterisk bucket underscore 0 underscore head, bucket underscore 0 underscore tail, bucket underscore 1 underscore head, and bucket underscore 1 underscore tail are initialized to none at the beginning of each bit pass. These variables will store the head and tail nodes of the 0 and 1 buckets. Asterisk inner loop, list traversal. The while current loop iterates through the entire linked list. Asterisk extract bit asterisk bit equals, current dot data bit underscore index, and 1 extracts the bit at the bit underscore index position from the current node's data. Asterisk next underscore node equals current dot next asterisk. Crucially important. We store current dot next before we modify current dot next. This is necessary because we are changing the linked list structure in place. Asterisk appending to buckets asterisk based on the value of bit, the current node is appended to either the 0 bucket or the 1 bucket. The logic updates the appropriate bucket's head and tail pointers. Pay close attention to how the buckets are updated. Asterisk in place removal asterisk. The previous pointer is used to update prev next when the current node is moved to a bucket. If current was the head of the list, self.head is updated to the next node. Asterisk current.next equals none asterisk. Very important asterisk. After moving a node to a bucket, we set current.next to none. This is essential to avoid cycles in the linked list. Asterisk update previous and current asterisk. We update the previous pointer to the current node only if the node was added to bucket 0. This is because if the current node goes to bucket 1, it is removed from the main list traversal, so the previous should not change. Current is updated to the next underscore node we saved earlier. Asterisk reassembly asterisk. After processing all nodes for a bit, the linked list is reassembled. Asterisk if bucket 0 is not empty, its head becomes the new list head. Asterisk if bucket 1 is also not empty, bucket 0's tail is connected to bucket 1's head. Asterisk the list's tail is set to bucket 1's tail, or bucket 0's tail if bucket 1 is empty. Asterisk if bucket 0 is empty, all nodes went to bucket 1, bucket 1's head becomes the new list head and bucket 1's tail becomes the list tail. Asterisk self.tail.next equals none asterisk. Another crucial step. Ensure that the next pointer of the last node, the tail, is set to none to terminate the linked list correctly. Important considerations asterisk. Asterisk in place limitations asterisk. In place algorithms often have more complex logic because you're directly manipulating the data structure's pointers. This can increase the risk of bugs. Thorough testing is essential. Asterisk stability asterisk. Radix sort can be stable, maintaining the relative order of equal elements, if implemented carefully. This implementation is likely stable but would require specific tests to confirm. Asterisk negative numbers asterisk. The code as written assumes non-negative integers. If you need to handle negative numbers, you'll need to consider 2's complement representation or adjust the bit extraction logic accordingly. You might need to treat the most significant bit as the sign bit and handle it separately. Asterisk time complexity asterisk. Radix sort has a time complexity of O, and K, where n is the number of elements and k is the number of digits/bits. In this case, k is the number of bits in the maximum value. If k is relatively small compared to n, example a constant, radix sort can be very efficient. Asterisk space complexity asterisk. Ideally, the space complexity is O, 1, for an in-place algorithm. However, the bucket head/tail pointers do contribute to a very small, constant amount of extra space. *debugging linked list algorithms can be tricky. Use a debugger, print statements to track pointer values, and draw diagrams to visualize the linked list structure as you step through the code. How to adapt for other data types. Strings. Radix sort can be used to sort strings by treating each character as a digit in a particular base, example ASCII or Unicode. You'd need to adapt the bit extraction logic to handle characters. Floating point numbers. You need to understand the IEEE 754 floating point representation. You can potentially sort floating point numbers by their bit patterns, but you need to be careful about the sign bit and how floating point numbers are ordered. It's often safer to convert them to integers or strings for sorting and then convert them back. Testing. Thorough testing is crucial. Create test cases with empty lists, lists with a single element, lists with already sorted elements, lists with reverse sorted elements, lists with duplicate elements, lists with a wide range of values, including the maximum possible value. This comprehensive explanation and code example should give you a solid understanding of how to implement an in-place bitwise LSD radix sort for a linked list. Remember to practice, experiment, and thoroughly test your code. Good luck.